FromDuel is a Swiss company delivering services around MySQL. Services means we do consulting. We provide support to discuss with customers why the system does not behave the way they expect it to, whether it's correct and the expectations are wrong, or otherwise whether it's a bug, which we then discuss with the manufacturer. We provide training around MySQL. And yeah, that's the consulting I think I mentioned already. When I talk about MySQL here, I refer to any variant of MySQL. So it may be the original as delivered by Oracle. It might be the branch done by Percona and called Percona Server. It might be the fork done by MariaDB called MariaDB. And it could be either with or without Galera cluster. So for me, and in the context of this talk, MySQL is a generic term covering all variants. As said, FromDuel is dealing with that and delivering services, member of the relevant open source companies or organizations, be they in Germany or in Switzerland. I personally have been active in the database management system development scene since I finished university. So I've been involved not on the application side, not on the application programming side, but rather on the vendor side, providing first a different database system, which was then later canceled decades ago. And I then joined the MySQL build team. Spent several years there, so those who followed MySQL release notes might have seen my name. I then worked as a database administrator with a larger website here in Berlin, and then joined FromDuel, where I'm working in support, in consulting, and will add training to it. Conferences are not yet counted as a separate activity. Well, that's my background. That's what I bring and what makes me talk about replication and Galera cluster. So what's the contents? We'll discuss a bit the MySQL server architecture so that you know what's happening where and how the various components interact with each other. We'll especially cover the MySQL bin log. And based on that, we'll discuss how replication is implemented and what Galera cluster does different. We will then compare those two approaches, and we will have some examples about circumstances when either the one or the other approach is a better fit for the customer, for the user. I'll discuss concepts. I'm not going into details or even commands and configuration parameters, so I'll try to show you the forest, not the individual trees. The basis is the previous GA version of MySQL. It is 5.6. I'm not yet discussing MySQL 5.7 in the main part of the talk. At the end, I'll explain to you why. As I said, it's valid for Percona and MariaDB. What I describe here does not include the so-called NDB cluster of MySQL, the special variant, especially for telco companies. And I'm not going to discuss the so-called embedded MySQL, where the application and the server code are linked into a single process, because that's fit for neither replication nor for Galera cluster. And if there's anything unclear and you've got a question about facts, please put it as soon as possible. There's no use in me continuing and some of you having lost the track and the connection. So factual questions, please, as soon as possible, discussion at the end. As I announced, the first chapter is the MySQL architecture in general. MySQL is a typical client-server system, so it does have one or more clients, typically on different machines, but might be running on the same machine, which somehow, either locally or via the network, communicate with the MySQL server process. And the MySQL server process is the only thing accessing the disks. The clients better do not try to do that individually or themselves. It would create a horrible mess, but that's standard for any client-server system. The server itself is multi-threaded, one thread per currently active connection, processing the commands sent by the client at the other end of the connection. And a disk, of course, includes rotating elements, or if you want it really fast and are prepared to spend the money, solid state. Doesn't matter functionally. In larger setups, it's very customary to have the disks in a SAN device, which has its own advantages and its own drawbacks. I'm not going to discuss them here. I trust you are all aware of that. Well, of the decision process to pick the one or the other. So the MySQL server internally looks like this. We have the client somewhere. Oh, sorry about the bad color combination. So the client is a separate process, typically several clients, of course. And whatever they send first is handled by the connection manager to make sure it's going to the proper thread. The user is authenticated, the commands are dispatched, queries or select queries might be served from the query cache if the results didn't change since last time. If not, or any other request is passed and then given to the optimizer for the best way to execute execution path. Access control is, of course, checked, and the table manager then picks the proper table using some caches, preferably, so that it need not do so many disk operations. And then it's passed through a handler interface, and there are several different handlers depending on the mechanism used to implement the table. What's interesting us here currently is InnoDB and nothing else. Everything else is a special solution, and the moment we talk about Galera cluster, or we can do only with InnoDB tables. I'll later tell you why. Yeah, that's the very high-level tour of the MySQL server architecture. Let's talk about the bin log, because this is where it becomes interesting. As I said, the server is multi-threaded, so we have got 2 or more user threads, each thread executing the commands sent by a single client. And the commands are then given to the proper table handler. In practice, table handlers are InnoDB and MyISAM. Others do not have a high usage number. That's why I did not mention them here explicitly. Now, before the command is given to the table handler, before it passes the handler interface, the lowest part of the general SQL layer is the generation of a bin log entry. The bin log means it's a collection of all changes which are done to either the data of the installation of the instance or to the schema. So any create table, alter table, insert, update, delete would find its way into the bin log and be written down there. That's not so much needed for recovery after a crash, but rather it's needed if you want to check, if you later want to check what was done when, who did it, and especially it is needed for replication, as I will soon show. Below that interface at the file layer, there is the table handler, and the table handler implements the access to the data on disk does the recovery after crash in the case of InnoDB if needed, and stuff like this. As those of you who deal with MySQL a bit, or who have more experience with MySQL, as those of you know, MyISAM itself is not crash safe. That's one of the nasty properties of the MyISAM engine and one of the reasons why you typically would not want to use it, from a few exceptions granted. Okay, so the important thing is that the bin log covers all changes, includes all changes and nothing else. It does not log select statements or any values returned. It just records the changes. Now, what is this good for? It means that in the bin log, we know, or we do log whatever was done to the data. So, or data or schema. And so this allows us to do recovery if we ever suffer a crash. We could start from an old snapshot and then apply all entries of the bin log, which were generated after that snapshot, and so do point-in-time recovery. We are not limited to the previous or the next snapshot, but we can reach any point in between as long as we've got the bin log entries available. It is independent of the table handler, so whether it's a MyISAM or InnoDB or whatever engine does not matter. It can be written in three different statements, in three different formats. The traditional format is the statement format, which means the SQL command is written in plain text. The new format is row, which means the old and new data are logged, but not the statement text. And there is the mixed as an in-between level. The difference becomes important because when you your statement might contain something which needs to be evaluated while it is executed. So when you say insert a row and the one value is a timestamp which you provide by the now function, then of course it matters whether you execute it just now or in 5 minutes. And the row format is essential to avoid any different contents which might be caused by functions like this. So the row format is the only one which really guarantees that if you apply the bin log later, you end up with the same result in the data as you did originally. With statement format, this can't happen, or with the data will differ. The bin log itself is written in segments. The segment size can be configured, and when one segment has reached its size, it is closed and a new segment is started. They are numbered, and this is pretty interesting very soon. The bin log is the basis for replication, and that's the reason why I did describe it in such detail. Replication means we want to do changes which were done on one instance. We want to repeat them, propagate them to another instance and apply them there too. So if both instances start from the same contents and I log all changes done on a master instance and send this log to the slave instance and apply the changes there, I will end up with the same contents. That's the basic principle of MySQL replication. So we have applications, clients, that communicate with one node, typically called the master node. And the master writes a bin log that contains all changes. And the slave starts from the same initial state. When we set it up, we simply transferred a snapshot of the data from master to slave and installed it there. Now the master, as I said, logs all changes. And the slave asks the changes to pass asks the master to pass all changes to the slave. The slave fetches all changes, or in other words, fetches the complete bin log contents from the master and applies those changes locally on the slave node. This is running asynchronous, depending on the relative speeds of master and slave, and if the commands are really complicated or the slave hardware is slow and its disk is heavily loaded or stuff like this, then we may have a delay in replication. So the data on the slave may have the contents which the master had some seconds or maybe even some minutes before. And in advance, we can't tell how much this delay might be. That's one of the weaknesses of MySQL replication. The other thing is, if any command on the slave behaves different than it did on the master, then the slave stops replication. Typical example, I do an insert into a table, and on the master it's all is fine, and on the slave I suffer from duplicate key. How could that happen? Well, quite simple, because somebody modified the data on the slave and already added that record. This can't be prevented in general. Now, what would an insert command do if it hits a duplicate key situation? The typical reaction would be the insert command throws an error, and it's the client application's responsibility to deal with that error. No problem, well known, any application that was programmed decently can do that. Now, if that happens on the slave doesn't have any connection to the client. The slave cannot return an error to the client application because the client application is not connected to the slave. It was connected to the master only. So the slave cannot return an error. On the other hand, it can't simply continue, which would be wrong either. So all the slave can do is stop replicating, throw an error, and call for the database administrator for assistance and help. Yes, you can do that, but if it happens in the middle of the night, most of you and your colleagues won't be very happy about it. Looking at it in a diagram, this is what happens. We have the clients connected to the master, not shown here. The master writes a bin log. There is a separate thread to which the slave connects and which it asks, please send me all changes. On a slave side, these changes are first written into a relay log on disk and then read by another thread, the SQL thread, which applies the transactions one after the other, and so does the changes on the slave. Typically, you would consider the slave to also write a bin log, and you would configure it to log the updates which itself receives as a slave. And if you do that, then this bin log here will contain all the changes the slave ever received. And if you have a proper setup and don't do any local changes on the slave, but just apply replication, then the contents of both bin logs will be the same. I said the contents, not necessarily the split into segments, because you could configure them different, say with different segment size. You could manually issue a flush command to switch to the next segment or stuff like this. So segment numbers and offsets in the segment may differ, but the contents will still be the same. And what do you do all that for? Well, the typical use is high availability. If you keep your data in both a master and a slave node, which don't share anything, please do not let them share the disk. Do not let them work on the same SAN unit, for example. If you have your data on both instances, then either instance may crash and your data will still be available. So you have high availability. The next advantage is you have got your data available in a second instance. So you could send any read command to that second instance and let that provide the values. Especially when you've got very complicated commands, joins across many tables, report generation about huge number of rows, searching for the customer with the highest order volume or whatever have you, then this may be a significant load on your database server, and you would prefer to have that on a read-only slave and not have it on the master node, which is also used to process all changes and enter all data. So we have high availability. We support a higher read load, also called a scale out. We, of course, have geographic redundancy if the two instances are located in different data centers. So you would make them independent of, say, loss of power, of a fire, of a flooding or stuff like this, provided the second data center is really separate and independent. You can use such read-only instances, especially for backups and for complicated reports. Report generation. You can, if you want to, configure your replication to add some intentional delay, which is especially interesting if you want to prepare against what my boss calls an oops query, the sudden drop table blah blah, which would of course also be propagated to the slave, and the table would be gone on both instances. But if you configure your replication for an intentional delay of, say, 60 minutes, there are good chances you discover it and stop replication, and so save your data and avoid the need to do recovery. And you can, in replication, do filtering. Filtering in a replication is possible, can be configured, is sometimes not really implemented correctly. I have run across some bugs in that and reported them. At the end, in the example section, I will show you one case where this filtering is really interesting and worthwhile. Returning to replication, it is not limited to a single level. So you can have a cascade, one master replicating to a first slave, and that slave using the same mechanism replicating to a second slave. Why is it interesting? Well, especially if you want to have your data on a huge number of slaves because you have an enormous number of reads, then you don't want to connect, say, dozens or even hundreds of slaves to a single master. You would bring it down to its knees just by sending the bin log to so many slaves. So you would have an intermediate slave for better fan out. In any case, the recommendation is that on the slave you configure it to be a read-only instance, and of course also to log its updates, otherwise propagating the replication further would not work. And you can have multiple slaves on a single master, but I would not go to really high numbers. So 2 to 5 slaves is okay, 20 is in most cases too much. Somewhere in between there is a limit, depending on the load and on the frequency of changes. Now, when you can cascade from a master to a first and to a second level slave, you can fold, no, sorry, coming soon. Yeah, the bin log, sorry about that. The bin log is identified by the log segment, file name, and the position in there, and the replication is configured by giving the slave the information where it should replicate from, so passing it the master name, the port to use, user password, etc., etc. And starting from MySQL 5.6, there is a new concept of global transaction ID, which makes setup of replication definitely easier because you need not deal with the position anymore. Global transaction IDs bring the feature of auto position, which makes it a bit easier. As I said, you can cascade replication, so you can even fold back that replication to the original master. Master, first slave, replicating onward to a node which happens to be the master instance. Now this looks like an infinite circle. No, it isn't. It is not infinite because any transaction in the bin log contains the server ID of the machine on which it was originally started. And this server ID is not changing. It's propagating onwards throughout replication. And typically you configure your machine such that the master will not apply any change which originated on itself. So this is where you prevent the circle from closing. What's a huge problem in a situation like this is if on both machines you do changes and those changes are overlapping. Because then they will both fail on the receiving machine and replication will break and your DBA will call for a pay raise for being awoken in the middle of the night. This setup, as just shown, is called a master-master replication, and opinions whether master-master is good or bad differ. I know colleagues who say master-master replication is really bad, don't do it. My personal opinion is master-master replication is perfectly okay if you know what you're doing and if you are configuring your application properly, and especially if you avoid overlapping changes. But it's not the subject of this talk to go into that in more detail. Anything else? Well, yes, what many people are not aware, a really big installation of replication, MySQL replication, is Booking.com. And with big installation, I mean Booking.com has master instances to which some 100 slaves are connected. Not on the first level, but on second or even third level. But they really serve 100 slaves from one master because they need to support such a high read load when people are looking for accommodation proposals. And if you want to go into replication and replication architecture in more detail and read about what's possible, even more complicated architectures than just shown, then I recommend a blog, or a series of blog entries written by Giuseppe Maxia, August last year, because he has shown several replication architectures and how to do it, what to avoid, and stuff like this. Recommended reading for those who want to do more than a single master-slave replication. So much about replication. Any questions? Yeah. The easiest way is to skip the transaction that did not apply on the slave. But of course, it depends on the cause for the trouble. So the typical example would be duplicate key. and the new insert will fail. Well, it doesn't really matter that much because the record is already present. Of course, you can ask both the slave and the master directly, do you have that record? What does it look like? If it's the same already, you would skip the insert. If it's different,
that would automatically heal the replication and it would go.
Yes. If you skip the offending transaction and then let replication continue, it will resume, it will proceed as fast as possible, and assuming that you are not operating your machine at the limit, it will sooner or later have processed the delay, and then they will be in sync as far as replication is in sync. There is always a small delay, but it should not matter.
And if I have a different situation, like something that maybe somebody removed the table from the slave,
In that,
I would not simply skip the step, but really have to get back to a state where it was healthy.
in that case,
Excuse me?
your best chance...
Excuse me?
Yeah,
Can
sorry.
you please repeat the question for the recording?
If it's not just a single row that's causing the conflict, but if, say, a complete table was dropped on the slave by accident, then you've got two things to do. The one is to make sure that it doesn't happen again by configuring your slave read-only, or revoking privileges, or educating your users, or whatever is appropriate. And the other is you would really have to set it up again. If a table was dropped on the slave, you would at least need to transfer that table again and then start resuming replication, which is, of course, a problem. It may be you would transfer the new contents of the table to the slave, which might be changed compared to the moment it was originally accessed, etc., etc. So this is not a trivial thing. The safest, but on the other hand also the slowest approach would be to do a total recovery. Transfer a snapshot from the master to the slave, together with a bin log position, which is valid at the moment this snapshot was taken, and let replication resume from that. That's possible, but it takes some time. Transferring an individual table is faster, but a bit more complicated.
So there's no magic switch like, please assure that the slave. So there's no magic switch that assures that you just tell the slave to roll up to the same state as the master. So fix all differences or something.
You can't do that because if the slave does not have the original data, you don't have a way to do that. There are third-party tools like the Percona tools which would help you in doing it, but using them and then resuming replication isn't any easier. The problem is you would get the new contents of the master and put it into a point in replication history which is some time back, and so you would put new contents at the place where old commands are applied, and this will again introduce the risk of replication breaking. But that's why it is so important to configure your slave instance to be read-only. And with MySQL 5.7, there is even a switch to calling it super read-only, which means even a user who has got super privileges cannot modify data on the slave. So that's maybe important. The fastest way is to use your networking functions. You would assign a virtual IP address and configure either the one or the other master node to react to it, to respond to that IP address. And your clients would use the virtual IP address. That's the fastest way of doing it. Okay. So that's about replication. Now let's continue to the other approach. As I said, replication does have some drawbacks. The first is it's asynchronous. The second is it's asymmetrical. You would configure at least one of the nodes to be read-only, even if you are running a master-master replication. So you would make sure that only on one node write commands are processed, because if you don't do that and write on both nodes or on multiple nodes in parallel, you may cause breakage depending on which data are generated. If one of the nodes crashes, then for high availability, you will need to do some failover so that the clients use the other node, as we just discussed, say by switching the virtual IP, but might be any other situation depending on which node is crashing. If a slave is crashing, the clients need not switch, but you might want to set up another slave or change your replication architecture if it's a bit more than a single master with a single slave. In any case, each individual node is a single point of failure for the slaves connected to that node. So if a single node that has got slaves breaks down, then you will need to do some change in the structure of replication. And doing such changes dynamically is a bit complicated because you need to handle the new setup point of replication, etc., etc. So it is possible, it can be done, it is done. Sorry, it is done, just consider booking.com, but it may be complicated. We would like to have something better, definitely. We always have wishes. We always want to improve or want the situation to improve. So we would prefer if the system were operating synchronously across all nodes, if it were symmetrical, and we could write on any node. We would prefer if the system would handle the would analyze and handle conflicts and not leave it to the DBA. We want high availability to be reached by the system just continuing to work without any structure change. And we want the system to handle the entry or exit of nodes dynamically without the DBA intervening. As I said, we always have wishes. Enter Galera cluster. Galera cluster is again a client-server situation. You have applications connecting through some network, typically by a load balancing mechanism, to several nodes of MySQL servers. You can have the load balancing mechanism with a single or with a traditional master-slave replication also, of course. But with Galera cluster, it's pretty essential because Galera cluster is about high availability, and you want to avoid manual action in case one node breaks down, so you want to have an automated load balancing or switch over mechanism. That's why I have it in this picture but did not have it before. Now, every node has its own local disk, and they do not share anything. What they have, however, is a replication layer which connects the code in all those nodes, and whenever any of the nodes is processing a data change, then it does communicate with its fellow nodes whether that change is possible or not. Because, as I wrote on the previous slide, we want to have automated conflict analysis on conflict handling. And this is why we need this communication here. Preferably, we would use a dedicated network just for the backbone so that it does not suffer from overload when too many clients connect, etc., etc. But that's more a performance decision and architecture decision, not needed on principle. And as I said, it's shared nothing. All the disks are functionally local to the nodes. It is symmetrical in that all nodes hold all data. It's not a split of the data contents across several nodes. It's a fully symmetrical approach. Now, as I said, it is based on InnoDB because for conflict handling, potential conflict handling, it must be a transaction-based table engine, and MyESAM does not handle transactions. So the data must be kept in InnoDB. It also transfers any changes done to the users, to the privileges, etc. These are, as several of you know, still kept in my ISAM database, but they are transferred via by command level, so the command modifying users, grant or revoke, create user, drop user, etc. These commands are replicated. The transfer of changes happens on commit only, not before. It is nearly synchronous and it is highly efficient. As a result, the whole cluster, Galera cluster, provides high availability in a symmetrical approach. As I said, all nodes hold all data. You don't lose transactions even if you have got a conflict. Okay, the victim transaction, of course, is rolled back, but any transaction that is successful is applied on all nodes in the cluster. Even if one of the nodes is currently down or out of reach, it will later apply the transaction too. Again, the cluster approach brings you read scale out, and it also slightly increases the write performance. Note that I do not use the term write scale out. Anybody who would promise you write scale out in a Galera cluster would be lying. The problem is every node holds all data, so every node must process all write commands. And if you have, say, dozens of nodes, obviously you can't have every node process write commands at full speed and then also do the write commands of the other nodes. That's impossible. Somewhere there's a limit what your hardware can do. And Galera does dynamically handle the entry or the addition or the removal of nodes, and Galera does take care of the necessary data transfer. That's important. You do not need the DBA to manually handle the initial setup of a new node. That's automatically done by Galera. The typical question which people ask is, how can it be so fast? How can it be nearly synchronous? Well, as I said, as long as a transaction is executing individual commands, insert, update, delete, they are handled locally on the single node to which the client is connected. And eventually, the client will issue a commit command, and in that moment, this node or the software on this node will send the whole transaction event to all other nodes in the cluster. For this, it uses the binlog code, not by writing the binlog, but by at least creating binlog entries. That's why you have to configure binlogged format to row in a Galera cluster. But they are not, it is not using the typical mechanism of writing the binlog to file and sending it to the other node and writing to relay log, etc. But what always causes those delays. But the binlog entry is transported across the network, say as piggyback on the commit node. And the other node is now checking, do I have any change that's in conflict? This check can be done pretty cheap because it's done by checking the primary keys. So the tables involved need to have a primary key, and in the commit entry, the primary key of all modified rows is transferred, and the other node checks, do I have any local command modifying, which just more, any local transaction which already modified them. Let's assume it did not. In that case, the node replies with an OK message. The originating node does the commit. The transaction is finished. The client is informed. The other nodes apply the binlog entry which they got here, piggybacked, which takes a bit more than the commit. So you've got a very small time window in which the nodes do not have the same contents. And after that, they are in sync. This is definitely much shorter this time than typically the binlog replication would need. And after that, they are in sync, and the transaction has been applied on all nodes. You see the source. I did not draw the picture myself. Well, nothing is really perfect, however much we want it to be. So there are some drawbacks. First of all, Galera is an addition to the original MySQL sources, which also means some delay. Currently, MySQL 5.7 is GA, is production quality as declared by Oracle, but there is not yet a Galera based on MySQL 5.7 available. That's one of the reasons why I use 5.6 as the base for this talk. Galera on MySQL 5.7 is work in progress. The second is if you have really very many modifications to a small number of rows, you will have a high number of conflicts. Now, when there is a conflict of transactions, the victim transaction will be rolled back and must be repeated, which means work is lost. To avoid that, it's highly preferable that if you have hotspots, you always modify them on the same node, because then the local locking of InnoDB will help, and this is much cheaper and much faster than a distributed conflict and the rollback of the whole transaction. You need at least 3 nodes, and if your database is really large, then the initial setup will take some time. Well, it will take a similar time in replication. No difference there. Let's again look a bit at the flow of control. The client accesses one server, sends a commit finally. This is replicated to all others. All nodes do what Galera or what Codaship, the company, calls certification, and it is guaranteed that all nodes will come to the same result. So either it is okay, which means on the originating node the commit will be done, and on the others it will be applied and committed, or it is not okay, which means it will be rolled back on the originating node and it will just be ignored on any other node. So much about Galera at a high level, Galera cluster. Now let's compare the two approaches, because both provide or want to provide similar features. They both want to provide high availability, and they both want to provide read scale out. So from that point of view, they are functionally pretty similar to each other. However, there are the details. As I said, both provide redundancy, both provide high availability, scale out, both provide instances which you can use dedicated for reports, for analysis, for backups, and both make the data available locally, say for branch offices. Now, what's the difference? Replication is standard. Galera is an add-on. Replication can use all table engines. Galera is limited to InnoDB. Replication is upwards compatible for one version, say 5.5 to 5.6 or 5.6 to 5.7. Galera prefers to have the same versions on all nodes, except for the moment of an upgrade, of course. Replication starts from 2 nodes, Galera from 3. Replication does fail over. Galera provides high availability without changes. Communication is slightly different, especially Galera cannot filter. It's always complete, it's always a fully symmetrical situation. When you have several nodes, you have slightly increased write capacity on Galera. If all writes go to a single master, then in any case, local conflicts will be handled by InnoDB. The statement will return an error. That statement will fail. The client will do it different or repeat or whatever is appropriate. That's fine. If you write to several nodes in parallel, you may have a distributed conflict. Galera will handle that fine. It will do a rollback for all but one of the conflicting transactions. Replication will break down. So that's one of the very important differences. Galera does handle a distributed conflict without the DBA intervening. Now assume your communication is broken for whatever reason. Network cable is torn or whatever. In any case, after a short interruption, replication resumes, and Galera does what's called an incremental transfer. It transfers the changes that have accumulated in the meantime. No real difference. With a long interruption, replication still resumes, but Galera may need a full transfer, a snapshot state transfer, if its cache for the recent changes has been exhausted. So with a really long interruption, Galera may need some time to resume operation.
How long is a long interruption? Minutes or hours or days?
It depends on your load. If you have one insert per hour, you can handle that interruption for days, maybe even for a week. If you've got 1,000 inserts per second, things are different. So there is a formula available on our web that shows how large you would have to configure your Galera change cache in order to survive which time of breakdown. When you add nodes or remove nodes, Galera does handle that automatically. If you add a node, Galera will automatically do the full transfer. Yes, it takes some time, but it works without the DBA doing it. And depending on the transfer method, the other node providing the data may be blocked. That's also one of the reasons why you need at least 3 nodes. The one reason is that all cluster solutions, including Galera, operate by some way of majority consensus of voting. So of 2 nodes, one may fall down, the other 2 will still see each other. They know we are 2 of 3, we've got the majority, we may continue. And the other reason is if that failed node comes up again and needs a full transfer, it will ask one of the other nodes to provide the data. This may block the other node depending on the method chosen. You can configure it. I won't handle that in detail here. And only the 3rd node will remain available for clients. So the system will continue to work, but of course at reduced capacity. Any distributed solution is limited by what's known as the cap theorem, be it replication, be it Galera cluster. You can't have all good properties at the same time. Just neither replication nor Galera can win against that. As I said, MySQL 5.7 is in progress as far as Galera is concerned. Replication is getting some new features. Oracle is working on group replication, which is de facto repeating Galera cluster work and doing it in Oracle, but Galera is definitely more advanced than a group replication. Group replication, for example, does not yet handle schema changes. Okay, I promised you a comparison or some examples when what not to choose. As I said, Galera is working by majority principle, also called a quorum, which means if a node is isolated and knows I'm 1 and we were 3 before, well, one cannot win against the other two. My data may be stale, I will stop working. By design, intentionally. It will not even provide data because they might be old and obsolete. You can change that by configuration, but it's rare that this is a good approach. And of course, when that isolation holds for too long, then there is a risk that the system might switch to the snapshot transfer, which is a slow operation for large data. Replication is different. Replication just accumulates some log segments and the slave will eventually ask for them, which means replication is more tolerant as far as communication failure is concerned than Galera cluster. It's easier because it will in general not need full transfer. As I said, replication can do filtering. A real-world example, we have a customer with head offices in Germany and factories distributed across the world. And they want the orders to be given to the factory by database means, but each factory should only receive the orders intended for that factory. You can do that by replicating and by filtering. You cannot do that in Galera because Galera is always symmetrical. So if you want to have such a selective propagation, selective transfer, you need traditional replication and you will add filters. On the other hand, if you have a conflict, as I explained before, replication will need administrator action. Galera will handle it all by itself. Advantage Galera. Hotspot, whether you are using replication or Galera, make sure that all changes to hot data are done on the same node, because then you will profit from InnoDB's transaction facilities, single row or row level locking, etc., etc. It's definitely much faster than having a distributed conflict, especially than having a conflict which the DBA would resolve. High availability, as I said, Galera will handle it all by itself, and it is faster in replicating, and it does not need a change of the master-slave communication structure, so it's easier to have high availability in Galera, provided your setup is suitable. Say you don't want to filter. Yeah, that's the high-level comparison when to use which or to avoid which, and that's what I prepared for here. Any questions?
We are running out of time, so we don't have really time for many questions.
What's the license on Galera?
GPL.
you mentioned that for avoiding hotspots, you should target writes to a single node.
Yes.
How does that interact with load balancing?
By proper configuration? Sorry, I can't give you any better answer. With traditional replication, you definitely don't want to have load balancing across everybody, across all nodes. You want to direct all nodes, all writes to a single node. With Galera, you could direct your writes to different nodes provided they do not conflict. Well, if they conflict, you get transaction rollback. You want to avoid that. It would work, but would be slow. But you should configure your load balancing, or you should configure your clients such that changes affecting the same complex. Say changes. You could have, say, order data and customer data and employee data in the same system. You would add customers on node 1, manage employees on node 2, handle orders on node 3, and you would set it up this way. And this would then also cover for hotspots.
Okay, thank you very much. For other questions, please catch Jörg Brühe at the coffee break.
Yeah.
Sorry.
I'll remain here.